built the audio amplifier, we built the oscillator, so there's just one section left, and it is this stuff here, Q2, which is the power amplifier mixer. The easiest way to see this is to look at this line I've highlighted in yellow. One person online I saw describe it as the magic bus, but it's connected directly to the key, so during transmit this is grounded. So you'll see this stuff here is gone, so if you look at just this part of the amplifier, that's just a standard Class C amplifier, and so it'll take the oscillator signal, amplify it, go through a low pass filter, out to the antenna, and you get some power out. On receive comes in, and we need to mix the RF signal here down to audio, and so this yellow magic bus is no longer grounded. It'll be, depending on your supply voltage, in the 7 to 8 volt range, and this large resistor here, or what does that say, R5 10K, this emitter resistor essentially sets the gain of the amplifier, and with such a big value, the gain is going to be very, very small, and so the transistor will act as a mixer. And I'll put a link to a document in the video description that goes into how this BJT works as a mixer in a bit more detail with some math and stuff if you're interested. But the RF comes in here, the LO will come in the base, and then from the emitter here we get the difference. This C9 here has a very high impedance at audio and a very low impedance above audio, so the F1, F2, and F1 plus F2 get shunted to ground, whereas the audio, which is F1 minus F2, is not, and that travels down this magic bus into the audio amplifier. So we will build this and then test it out and make sure that we can transmit and receive, see how much power we get out. But it looks like all the holes on top are filled, so don't see any light shining through. In theory, we have a working Pixie now. So we will hook it up and test it out. Got this hooked up, headphones, key, 50 ohm dummy load, and we can plug in power, and if we key down, and if you can read that, it's 14.8 volts peak to peak, 5.1 volts RMS, so that's half a watt, because it's RMS squared over R, so 5 times 5 divided by 50 is about well, it'll be slightly over 25 divided by 50 is half a watt. So that's probably about what you'd expect for a Pixie like this. We can also, yeah, that's good. We can also listen on the KX3 here, see what it sounds like. This, I just got this little piece of wire here to help pick it up as we transmit into the dummy load. So if I key down, I just gotta find what frequency I'm on. It sounds fine, not a whole lot of chirp. So that's good. Next I'll switch where put the dummy load on the KX3 and put the wire on here. We can transit with this and see what we hear coming out of the whatever this is called, the Pixie. So now I got the Pixie hooked up for the receiver. Turn it on. I don't have a good speaker, so I'll just record it and I'll have to put the audio in post-production. But if I key down, I might have to tune around to find where this is listening. This is the local oscillator that the KX3 is picking up. And I can hear both sides of 0 beat. This is the low side. If I tune to the other side. So, everything seems to be working. So this is the spectrum of the Pixie output. I just took a snapshot on the oscilloscope, saved it off on a thumb drive, put on my computer, and I have some Python scripts that will compute the power spectral density, which is what we're looking at here. So you can see this first peak here. This is the signal we want at 7 megahertz. And then this second harmonic here at 14 is well above the FCC limit, which is this red line. However, the third and fourth and all the higher ones are definitely below it. So you probably should alter the filter a little, put like a second harmonic trap or something in there, try and knock that down if you want to put it on the air a lot to keep it totally legal. This is not a whole lot of power. This is even less. You know, it's unlikely people would hear you on 20 meters if you're calling on 40, but it's still better to follow all the FCC rules. Well, in order to try and knock down the second harmonic, I tacked on this capacitor here, which is in parallel with the inductor in the low-pass filter, to create a second harmonic trap, and it seemed to work pretty well. By my math, I needed a 128 picofarad capacitor, and the closest I had was 120, but it seemed to work when I put it in, and I'll show you what the power spectral density looks like. So once I added the 120 picofarad capacitor, ran it through the same script as I did before to get this plot, and you can see 7 megahertz looks the same. 14 megahertz is well under the limit. The third and fourth harmonics have grown a bit. I think partly that's because I recharged the battery. I was using to power this between the original and the new filter, so the supply voltage went from about 11.5 to 12.5 volts. So I think this third harmonic would drop below the limit if the power supply was reduced a little bit. And my guess is this fourth harmonic popped up because there's some sort of interaction with the second harmonic trap. So I'm not too concerned about it. This will be up in the 10 meter band. But I think this is a lot better than the default filter, and it was a pretty easy fix. So I'd recommend just adding a 120 picofarad capacitor in series with the inductor if it's the same value. Mine was 1 microhenry. The document linked below has the math to work out exactly what value capacitor you want. So check that out if you want to find it exactly.